So, so our remaining problems are that if we don't have a sorted list, we need some non-centralized algorithm to decide who should be the next centralized process. Okay? And different consensus states possible even if ID is used for switchover. And in general, we could use the voice of more than one member. Okay? So what we're going to do is we're going to go to Paxos, okay? And we're going to try to figure out how we can do. So the question we're trying to answer is how to detect and sequence concurrent requests. And the algorithm we've seen so far is, like I said, an autocracy. And we want a democracy, we want a parliamentary system. And the person whose algorithm I'm going to describe is the guy called Leslie Lamport. And Leslie Lamport is somebody who actually visited UNC decades ago. Seems to me only a few years ago. And he gave probably the best theory talk I've ever seen. His talk was all a bunch of was basically like a slideshow, and it was so clear. He didn't give the talk on this particular subject. He's been doing other things too. And this Paxos algorithm actually, so why the word Paxos? Paxos is a region in Greece, and it was supposed to have a fictional consensus system, which is very parliamentary. So that's why the word Paxos was given. And this algorithm was concurrently discovered by both Leslie Lamport and Barbara Liskov. Barbara Liskov is at MIT, and they too won the Turing Award. So this is these are very smart guys who come up with these algorithms. I believe the first one to write, or maybe the only one to write up this algorithm, was Leslie Lamport. And when he first wrote the algorithm, he would go after the algorithm was published. He would go to theory conferences, and people say that's too complicated. We really don't understand it. Okay, so then he wrote another paper called Paxos Made Simple. And if you go and search for Paxos, you'll see that people have been spent a lot of time trying to simplify Paxos Made Simple. Okay? So what I'm going to present to you is my simplification of his algorithm. And he thinks that it's among the simplest and the most obvious of distributed algorithms, but he's a big fan. So how to detect and sequence concurrent requests? In the with monarchy, you go and a single replica decides, and now multiple processes decide. Okay. And that's not entirely strange, even in our previous algorithm. They were deciding whether to accept a value or not. Okay, whether a particular individual value should be accepted or not. So why not go and give them one more piece of information that given two concurrent proposed values, which one should be chosen? They were making a decision together about whether a specific value should be accepted or not, and they voted. How about deciding between two proposed values and saying, okay, this is the proposed value we will consider for acceptance, and this value we'll reject because of concurrency conflict. Okay. And we can imagine both an asynchronous version and a synchronous version, but it doesn't make sense to have an asynchronous version because the asynchronous version just comes freely. We are asking everybody about concurrent proposed values. So why not even ask them whether a particular value should be accepted or not? Okay, we are sending we have that phase anyway. They can always say yes. So an asynchronous version doesn't make sense from efficiency point of view. Okay, the only reason asynchronous case makes sense is when we want efficiency, because synchronous case reduces to asynchronous if everybody says yes. Okay, so this is our centralized case, and we want to get rid of the central bottleneck. And how would the arrows change to support the parliamentary system? Right now, the proposed messages go through a central process, which goes and sends accept requests, receives accept responses, and sends learn notifications. So this particular process is responsible for many tasks. Okay, we want to get rid of this particular process. We are still going to have multiple phases, because we'll still have to go and check with a bunch of acceptors whether a proposed value should be considered or not, because for concurrency reasons. So somehow we have to go and take these green, red, and purple arrows, which will still remain, and attach them somewhere else to get rid of this particular process. So think about that now. Okay. This is distributed synchronous. So we go and so the previous slide showed you what happened in distributed synchronous, and we go from distributed synchronous to Paxos. So this is what David said, that the purple arrows go straight from proposer to the acceptors. And like Chris said, the red arrows go from the acceptors to the learners. Okay. So now the learners will have to make a decision. Now they're getting multiple values, and they'll have to go and choose somehow the correct value. Okay. So this is towards basic Paxos. This is not quite the architecture we'll end up with. And we'll try to derive this algorithm so that we understand it deeply. If I was to just describe the algorithm as presented, it will probably take me only 15 minutes. But I'm going to try to derive it, which means it might take me another 45 minutes. I'll see how far I can go. And again, as before, if you guys need to leave, you can leave. But any extra time I use will go towards making up for the time we've lost earlier. Okay. And I guarantee you, I won't try to make up more than the time we've lost. Okay, so let's try to come up with an algorithm gradually using this architecture. And let's go and see what we're trying to guarantee and what Paxos guarantees. So earlier I said, look, we'll assume TCP IP, we'll assume messages are not lost and they are sent in order. As it turns out, Paxos is so powerful that it can assume delays out of order and delays. It can deal with both out of order and losses. Okay, but we're going to make a very simplifying assumption. We'll assume that the value to be changed is a final variable. That means it's either pending or uninitialized, or it has a value. It once initialized, it cannot be reinitialized. That's what I'm trying to say. Okay. And why is that practical? Well, as it turns out, you can build a practical algorithm on top of it. Okay, we saw that in the centralized centralized algorithm. When one central process fails, we need a way to go and elect a new central process. And if we don't use a priori order, we might just go through one round of Paxos and try to figure out who the new central process is. We start off by having the central process uninitialized, and as soon as the value gets initialized, we are done. We're not going to change the value again. So Paxos algorithm is used with some other algorithm to go and create multiple, to change the same object multiple times. But in this algorithm, we'll assume that the value is written only once. Okay. So all learner commits have the same proposed value. It guarantees that. So they go from pending to value, and that's the only state transition they make. They don't go from one value to another value. And a learner side commits to this value when and if it receives acceptance from a majority of known acceptors. Okay, that's what we'll end up doing. Okay. We look at various versions of this algorithm, but this is what we're going to do in the end. And I think through all the intermediate algorithms also, I go through this particular constraint. And not only can messages be delayed and be out of order, but nodes can come back up and messages can be retransmitted. So we will make sure that eventually all listeners will commit to the same value, or some values will be uncommitted. Okay, we won't have different learners commit to different values. That's the guarantee we'll give. So let's come up with a very simple algorithm first. Okay, so Lamport says that, look, the algorithm follows from the properties of distributed systems. Okay, So I'm going to come up with a series of algorithms that don't follow from the distributed properties of distributed systems. And let's try to find flaws in them to converge to the right algorithm. Okay, that's how I understand things, and that's how I assume a lot of you understand. Okay. So here's my initial algorithm. I said that an acceptor decides among multiple proposals which proposal wins. Okay. So we are going to change the value only once. Okay. So if there's only one value proposed for it, then things are very easy. And things get difficult when there are multiple values proposed for it. So when there are multiple values proposed for something, each acceptor could accept the first proposal it gets. Okay, this is a straightforward generalization of what we saw in the centralized case. The centralized process that we saw accepted the first value and the second value, which went and sent a concurrency conflict message. Okay, so this seems reasonable. And a learner learns the value that has majority acceptances. Okay, that's what I said earlier in those bulleted slides, and that's what we can. Okay. Now, if this was the algorithm, we'd be done. Okay, I wouldn't be threatening you with 45 more minutes. Okay. So, what's the problem? Well, different acceptors can get proposals in different order. Okay, when there was a central process, then the order in which that central process received values was the order. Now, different acceptors can get proposals in different order. Okay. Acceptances may arrive in learners in different order. So, different learners may use different majorities. Okay. So, assuming that this first problem doesn't exist, that all acceptors uh, get the proposal in the same order. Okay. Can this cause a problem? So my question really is, can different majorities agree on different values? Let me make the question more concise. That given that a learner learns the value that has majority acceptances, okay, and given that a value is accepted only once, okay, given these two constraints, okay, let's just forget about this for a moment. Given that um, an acceptor accepts a value only once, a learner learns the value that has a majority acceptances, we can have the problem that can we have a problem? We can have the problem that different majorities maybe may so different learners may use different majorities. Can different majorities agree on the same different values now? That's my question. Okay. So one learner gets the value from 1, 3, and 5. Another learner gets values from 2, 3, and 4. And can it be the case that these two learners will learn different values as long as an acceptor does not accept more than one value? Okay, this might be a very straightforward question. I've spent a lot of time explaining it, or it might be a complicated question. Okay, so let's go and try to. Each pair of majority will have at least one member in common. In my example, I said 2, 3, and 5, and 1, and 2, 4, and 3. So 3 was common. So if 3 could change its mind, then indeed we could get different majorities having different values. But since 3 is not allowed to change its mind, okay, uh, we are guaranteed that the same value will be agreed on. Okay, so we are actually fine. Okay, as long as um, this particular uh, so the answer is they will always agree on the same value. Okay, now let's look at the remaining. Okay, so the next question is, can different majority can is the majority always guaranteed? And two proposals may get the same number of votes, okay, depending on the order in which they arrive. So we can go in. Sorry. If we have an even, so there are two problems here. First one is that we might not have an odd number of uh, acceptors. Okay, so two proposals may get the same number of votes, so we can choose an odd number of acceptors. But given n acceptors, it's possible to have n concurrent proposals, each of which wins in one acceptor. Okay, there's no guarantee about the order in which messages go from different proposals to different acceptors. There's no central process, so they can follow different routes. The two cars can start at the same time and reach different destinations at different times. So or the same destination at different times. So so that's a problem. Okay, so that's the next problem we need to. So let's go back to this slide. Each acceptor accepts the proposal with the highest number it will see. Learner picks the value that has majority acceptances. That's what we have. And the problem here is that we can't see in the future. Okay. So so what we do instead is have the acceptor accept a proposal if its proposal number is higher than what it has seen so far. So like I said earlier, this is like somebody interviewing a bunch of candidates, and each time they see a better candidate, they go and fire the previous one and hire the new one, which is something we don't want to do, which is something you don't want to do in real life, but it can cause a problem because acceptor is changing its mind. Okay, and when an acceptor changes its mind, the problem is that a learner is picking the value that has majority acceptances, and two different majorities may now agree on different values. Okay, so so uh, so so different learners can get different majorities, and common members may have changed their mind. So we cannot agree on a common value because so this is the situation that Randy was talking about, where now we have two different majorities. Earlier, the two different majorities had agreed on the same value because no acceptor could change its mind. Now an acceptor can change its mind, so we have a problem. So we can't allow acceptors to change their mind. That's the point I really want to make. Okay, I was trying to make some intermediate points in those slides, but this is really the point I want to make. Okay? So we can have different learners pick different values. Okay? So we run into a problem. Okay, the problem is that given the constraints I have, we can't quite solve the problem. Um, if we have the acceptors change their mind, then different majorities can agree on different values. So that's a problem. And if acceptors don't change their mind and just pick the very first value, then we may not have any majority. Okay. So how do we solve the problem? We don't change the behavior here. We have never changed the behavior here. We've tried to change this behavior multiple times. We said, pick the first value, um, keep changing your value, pick the first value and freeze it, keep changing your value based on what the proposal number is, and that causes problems here. Okay, we're going to try to go and change the behavior of this particular process. Okay, and we're going to do so by adding another phase. So we're going to and try to imagine what this might be, because that's the key idea that I want to go to next, and I hope you guys are fresh enough to for someone to go and try to answer this question. But let's change this behavior. So far we were just proposing the value, and that was the end. Okay, we're going to be a little bit more careful about values we propose, and so we're going to perhaps add another phase here where we just don't propose a value. We think a little bit, we send a bunch of messages, and based on the responses to these messages, we actually go and we decide to propose a value or not. So we add a new phase, and we add a new phase by creating changing the behavior of the source. So can you guys imagine what this new phase might look like? Can you sort of try to guess what the steps might be? So the key idea is that a proposer does not play spoiler. A proposer does not override consensus that may be achieved from an earlier proposal. Okay? And to determine if there's another proposal, it goes through an extra round. Okay? So the proposer needs to know distributed state before proposing. So like Chris said, they talk to each other, and based on what responses they get, they go and decide to propose a value or not. Okay? And what is the distributed state? The distributed state is in the acceptors. So each acceptors has seen some previous proposal. It knows about the last proposal it has seen. It knows about the last proposal it has accepted, and the last accepted value at each acceptor. And the last accepted value. So at each acceptor, the information consists of the last accepted proposal, the last accepted value, and the last known proposal. So we have one proposed phase and two overall. In Paxos. In the modified Paxos that we have, sorry, in the basic Paxos that I showed earlier, which is not really Paxos. Okay, now we're getting towards Paxos. So that was just an initial algorithm. So now what we'll do is have two proposed phases. Before sending the actual proposed value, a proposer will go and query each acceptor, get responses back, and based on these responses, it'll actually go and propose or not propose. And the value it will propose will be based on the responses it gets. So like Chris suggested, it might actually change the value it proposes based on what it has seen before. Okay, that's going to be a key idea here. So we've been motivating and describing Paxos. We spent most of last lecture doing so. We'll spend all of today's lecture, however long it takes, to finish up this. And this might seem a lot of, this may seem to indicate that Paxos is really complicated, and in some sense it is to understand it deeply. But to get the gist of it, you can probably see a YouTube video of 15 minutes to understand what's going on. From what I remember when I first approached this topic, I found that the YouTube videos are quite short. So this is much more detailed than what others have presented, and perhaps much more detailed than necessary to understand the gist of how it works. But I'm trying to design the lecture in such a way that I can get you guys to help derive the algorithm. So we started with the idea of having a decentralized system. Okay, so where we want concurrency conflicts to be caught without having a centralized process. So who decides whether a particular proposal goes through, whether it has a concurrency conflict or not? Not one centralized process as in assignment 7, but a bunch of acceptors. Okay. So you propose, and they decide whether your proposal goes through or not. And in two-phase commit, the centralized process went and then broadcast to all the learners what the verdict was. So each one of them goes and broadcasts to all the learners what each one's verdict is. And the learners then go and aggregate the verdicts from different acceptors to figure out what should be done. Okay. So that's not quite the Paxos architecture. It's towards Paxos. And I'm calling it two phases, and that's the terminology that I use. That's not what Lamport uses. But by a phase, I mean a broadcast. Okay? So often the word phase is used to describe the state in a particular process. Okay, so if a particular process does two broadcasts, one followed by the other, then it's in the first phase first and the second phase next. Here it does a broadcast, and these guys do another broadcast. So there are two broadcasts, but done by different processes. So that's what we started with. And we wanted to make sure that learners did not learn different values. Okay. So that was the goal. And one rule we came up with was, we came up with many rules, and the one we converged to last time was that an acceptor will accept a proposal if its proposal number is higher than what it has already accepted so far. Okay? And it broadcasts acceptance to learners. And if it doesn't accept it in the implementation I'll describe, and maybe even in the timing diagrams, the acceptor can go and send a message back to the proposer saying, hey, I rejected your proposal. So that's optional. And learners' response in all the versions of the algorithms we'll see will always be to learn the value that has majority acceptances. Okay? And hopefully it won't learn multiple values. It might learn the same value multiple times, but it won't learn multiple values. Okay? So how to ensure this? These two things seem at odds with each other. The goal of not learning multiple values and allowing an acceptor to change its mind. Because what could happen is that the acceptor could accept one value first, then another value, and all acceptors could do that, and the learner would learn different values. So, for instance, all the learners might first learn the proposal value associated with proposal number 0, then proposal number 1, then proposal number 2. So we are learning multiple values. Okay. So we talked about this last time. And we said, look, we won't change the, uh, we will change the acceptor to some extent, but we need to do more than just change the acceptor. Okay, we need to also control what's happening at the source rather than what's happening at the sink. So we'll say that the proposer does not play spoiler. So the proposer does not override consensus to be achieved from an earlier proposal. That's the goal. But how does it know that? Okay. If it knew that, it wouldn't cause a conflict. So it has to go and learn that information. So it has to know before it proposes, it tries to learn understand, not learn quite in the sense of the learners, but it tries to understand the distributed state before proposing. So the question is, how can we change source rather than the sinks, the acceptors and learners? Learners really the sink, that won't change. So how can we go and change the source, in addition to perhaps changing the intermediate nodes of acceptors? So this is where we go from this architecture where there were two broadcasts and one phase in the proposer, okay, two phases overall, okay, to three phases. So before this actual proposal goes through, and I'll call a proposal also a request for accept, so I'll also call it an accept request. So before it sends the accept request, it tries to query the state of the acceptors. Okay? So that's the pre-proposal state and what Lamport calls prepare. Okay? So it sends a prepare message to each acceptor. Each acceptor sends a response not to all the learners, but individual responses back to the acceptor. Okay? And based on these responses, the proposer decides what next to do. Okay? So now it's got more information, and perhaps we can come up with a correct algorithm. So the proposer sends a prepare message with the proposal number only. It doesn't need to go and send the value. And Lamport says that you can send it just to the majority of acceptors because all you're waiting for is majority consensus. But to be more robust, we should send it to all acceptors. Okay, so it will work either way. There's more chance of progress with sending more messages. Okay, so there's a safety property, you don't want to do something wrong. And there's a progress property which says that you want to converge to the final value as quickly as possible. So you're trying to query the current state of the acceptor. You want to try and decide what happened with any previous proposals that have gone through, any prepare messages, any accept messages. And the acceptor goes and responds with a summary of past prepares and proposes. Okay, so this is a question. This is the general idea. The details are what's interesting. So we have to figure out next what the summary might be. Okay. And it uses responses of majority to determine if it should send a proposal or not. And if it sends a proposal, what value it should propose. It could be the value it had intended to propose, or it could go and propose some other value with a previous value, as we saw last time. And it'll, of course, choose its own new proposal number for that value. Okay. So let's try to spend some time trying to figure out what might be information that goes into the summary and what might the proposer try to do with the responses. And if you get that, I mean, it's brilliant because we've got the algorithm, but I suspect that it won't be that easy. So let's try to see what we can come up with so that we understand what represent later a little more deeply. Okay, so I think that's the next question. And we'll keep this we'll keep this, and so the hint about what to do here is right here. This is something I've reproduced from earlier, that each acceptor accepts a proposal if its proposal number is higher than what it has accepted so far and broadcast acceptance to others. So the key is this particular sentence, and that can hopefully go and help us answer these two questions. So I see Randy's already raised his hand, so let's just go to the student discussion slide. So we saw 4 answers, 2 for this and 2 for this. One answer was that what Leo said was that the acceptor sends a list of all proposal numbers higher than the proposal number in the prepare request. And Jason said, no, just send the maximum. And sending the maximum value is a summary. And we saw 2 answers here. So one was that if the proposal number has not been seen by the majority of acceptors, then we go and use that proposal number that we had intended. And then the other answer was that if any acceptor has seen a higher proposal number, then don't use that proposal number. Okay, so we'll try to go and punt on this a little bit. Since the acceptors look at the highest, proposal number, I think we can go with Jason's suggestion of just using the highest proposal number rather than using the whole list of proposal numbers. Okay, so because the two I don't want to overload the word proposal here, but the 2 suggestions were to look at the highest numbers. And if you're looking at the highest numbers only, then we don't need to send the whole list. Okay, and we also have the last accepted proposal number and value. Okay, so why not send that too? Who knows? That might be useful. Okay? And so this is the state that the acceptor keeps, and this is not an unbounded state. Okay, so just 3 values to be kept. Doesn't depend on how many proposals it has received. So we'll just see that we keep the highest proposal number seen before this particular accept request was made. Okay, prepare request was made, and the last accepted proposal number and value before this prepare request was received. Okay, and we'll punt on whether David was right or Jason was right, and we'll say the following. Oh, actually, no, we're going with David's. If some responding acceptor has seen a higher proposal number, abandon attempt. Okay, the majority may not have been achieved so far, but it may be eventually achieved. So why not just abandon the proposal and let that majority be achieved? Okay, because there is somebody with a higher proposal number around, and yes, if they go and fail, then hopefully they'll come back and repropose. That's the assumption here, that when node fails, it keeps recording what it has sent so far. It eventually comes back up and reproposes the value. So why should we, we're not going to win here. Okay. So we don't even have to, so we can go and just wait for majority responses. And if some responding acceptor has seen a higher proposal number, abandon attempt. Okay. Eventually, the majority of people might see this proposal number. So this is safe. And this is clear. Okay. If no responding acceptor has accepted previous proposal, okay, seems very safe. or seen a higher proposal number, then propose the intended value with the intended proposal number. Okay. So far, so good. Seems safe. Okay. Well, not quite. So I'm claiming here there can be race conditions. Um, it's not, this is not sufficient, and we can change no to this majority, and it still would not be sufficient. Okay. So can you guys see the race conditions that might occur? So 1 and 2 can both find this condition and propose their values, because remember that they go and neither, supposing 1 and 2 start and they both send their messages before either of them has started the accept phase. Okay, so then each of the acceptors will go and say, oh, I haven't accepted any value so far, I haven't accepted any proposal so far. And so they will go and say nothing accepted so far. So both 1 and 2 will go and propose values, and that will cause will then cause uh, multiple values to be accepted. Supposing 1 goes and sends the accept request first, then the acceptors will go and accept 1's value. Then 2 will go and send its accept request, and each acceptor will say, oh, 2 is greater than 1, so let me accept its value too. And now 2 different values are learned. Okay. So majority of acceptors could get and accept VP1 first and then VP2 later. Okay. And two majority propose different values. So because acceptors are changing their values, and because we haven't gotten to the accept phase before both prepare phases occurred before any accept phase started, we are in trouble. So here's the situation. So we have 3 nodes, 1, 2, and 3. Okay. 1 wants to send a request 1, 42. So it wants to go and send the number 42 as with proposal number 1. 3 wants to send the value 29 with proposal number 2. So they both send their prepare requests. 1 sends a prepare request. So 1, 2, and 3 are proposers, learners, and acceptors. Okay, and when a node is both a proposer and an acceptor and a learner, these lines become tricky. So this one is saying that this message goes to itself, maybe to a separate thread, which responds by saying, look, I've seen nothing so far. Okay, so the before you, I saw no proposal number, I've accepted nothing, I've accepted no value. Okay. 3 goes and sends the same message to itself and says, look, everything is uninitialized. Okay. Once prepare request goes to 2 and eventually will go to 3 also. In all the examples, I don't show the message going to 3 because it just creates more clutter. It goes and says, look, I've seen nothing so far, accepted nothing so far. Then 3's prepare request goes, okay, and its response is, look, I've seen 1, okay, but we're not really using 1 in our algorithm. This is just something for future, but I've accepted nothing so far. Okay, so both of them are question mark, question mark. Okay. So 1 gets 2 responses with no accept. Okay. And even if we were to use this number, this number is uninitialized here. Okay, so I said that, look, I'll make your task easier by saying that this particular number, the proposal you've seen so far, highest proposal you've seen so far is not used, because that's in Lamport's algorithm, that's not used actually. In the one that he gives for safety, then he does go and indicate later that for progress you might want to use this. So even if this value is not being used, this guy goes and says, oh, majority of people have not seen 1 and not accepted anything. So I'm going to go and propose 1, 42. Okay. So propose is the same as sending an accept request. That goes to 2. 2 says, fine. I haven't accepted anything so far. My rule is that I will not accept anything that is any proposal whose value is less than or equal to something I have accepted before. Less than, actually, because if it's equal to it, it won't get a duplicate message, hopefully. Though Lamport's algorithm does allow duplicate messages to be accommodated. So it broadcasts accepted to the world. So 3 also gets 2 responses with no accept. Okay, so it gets its own response back. It gets 2's response back. Okay, that's majority. It doesn't have to wait for 1's response. Okay, so we don't even show the message going to 1, just to reduce clutter. So it goes and proposes 229, and we have the problem that we had before, and that will get accepted too. Okay, so regardless of whether we use this number or not, we are in trouble. Okay, so what should we do? Okay. So this will go and so this node has gone and accepted the value, 2 different values, which is something we didn't want to have. Okay. So 2 accepts 2 values, as will 1 and 2 as will 1 and 3 actually. Okay, so this should be 3 when they get proposes. So 2 different learned values. Okay. I initially went and made this node 1, made this node 2, made this node 3, because that way we know that proposal number 1 is from 1 and proposal number 2 is from 2. But I later show you traces. But then things don't get in order here, and later I show you in traces of code I've actually implemented, which was inconsistent. So you'll sometimes see me calling this 3 and this 2. So I hope I remember to go and change this 2 to 3. Otherwise, you guys can just listen to the recording. Okay. So how to fix problem? Okay, so the key is that this response had this 1 in it, and this response had this question mark in it. Okay. So can we go and use the fact that this response was given in a different state than what it was when this response was given? And can we use that logic to make sure that the acceptor does not accept 2 different values, even if they get proposed? So we won't go and change the proposers. We'll change the logic at the acceptors. The acceptor knows that there has been a 1 after a question mark. It should know after this question mark that it'll get an accept request with 1. It should know after this particular message that it'll get an accept request with 2. So can it do something to make sure that it doesn't go and accept this request? So we change the logic here. Okay, I think I've more or less given the solution away, but let's go and see. Maybe it's still tricky. So I think I have a discussion slide next. Okay, let's go and answer the question gently. So before I go into David's solution, which says that based on the prepare requests, it should go and reject certain proposals, which is kind of what I was hinting at. We still don't have the exact algorithm, but we could go and say that, look, whenever a proposal, so the question is, in the previous slide, should it accept 1's proposal or 2's proposal? So 1's prepare request came first and 2's prepare request came next. So we could say that 1's prepare request just locks the node, and it won't go and accept anything after any proposal after that. We could just say that. Okay. So lock distributed state by requiring each responding acceptor to not accept future proposals. Okay, which means prepare becomes block. Is that a good idea? And I'll just go into the answer. So if the proposer dies after locking, no other proposer can propose. So even if we could magically lock that state, we can't. This is not fault tolerant. Okay. And if locking was so easy, then why didn't we use locking in the first place? We don't have to go through. I mean, this is a recursive problem. The problem is, how do we lock? Okay, and so what if Some acceptors lock node 1 and then lock into node 1's proposal, and some acceptors lock into node 2's proposal. What is a lock? Majority. So it gets all very confusing. Okay. And main thing is that we don't want, the proposer dies after locking. We don't want that state to be locked forever in the acceptor. Okay. Let me draw an analogy with the test and set instruction to understand what we need. So the test instruction just retrieves data, okay, in particular lock status. Test and set both retrieves data and sets the data atomically. In particular, it allows us to go and determine if something is locked, and if not locked, make that region locked, and do this atomically. So far, we have considered this to be a query that just returns data. We have been doing only test because we have not been actually locking. We are just checking the lock status. We want to go now from only test to test and set. So this is the test part, where it's returning some data. And this is the set part. Okay? This is the part that achieves the kind of locking we want. So when this proposal arrives, it compares its proposal number with the highest number it had seen previously. And if this number is higher than any previously seen number, then it stores the value in its state. And that's how you can actually return this get part correctly. You do have to do some storing to return these data. And it then promises, this is the locking part, where it won't accept any proposal lower than this. Okay? So this is the number, highest seen proposal number before this proposal, and this is the highest number after this proposal was received. And we don't know whether we need all three values here, but let's keep them all. Okay? Maybe just two of them are enough. And we will not change the proposed stage here. So previously the proposal was each accepted proposal if its proposal number is greater than what it has accepted so far. Now a proposal accepts a proposal only if its proposal number is greater than or equal to, it doesn't matter because equal to means the same proposal, what it has seen in prepare request so far. Okay, and then broadcast acceptance to learners. Okay, so we've gone from last accepted proposal number to last seen proposal number, which is kept at the acceptor. Okay. And the last seen proposal number when the accept request arrives. So let's go and see what happens now in this with the same kind of timing. Okay. So we see the prepare request being sent here. Okay. And we see that this particular node 1 goes and sends a proposal number 1 with 42. Okay. After this prepare request is received here, so let's go and see what I have. Proposal number in 1's accepted request is lower than highest seen proposal 2, so rejected by 2. Okay. So this particular proposal will be rejected because it has gone and seen, because this one was sent after this 2 was sent to it. Okay, so this node remembers this 2, and then since 1 is not equal to or greater than 2, this accepted request gets rejected. Okay, so we achieve the goal we wanted. Okay, so it's not that the first request gets accepted; it'll accept the proposal request with the highest proposal number that's greater than what it knows about. And this node, on the other hand, its proposals will get accepted by everybody because its proposal number is greater than or equal to what the nodes have seen so far. It's the highest proposal number so far. Okay, let's go and change things a little bit. Let's say that 3's prepare request arrives late. Okay, so node 2 has accepted 1's proposal. Okay? Because the prepare request came later. Okay, it comes later to both of these two nodes. Okay, so this node is accepted 1, this node is accepted 1. Okay, now when this request arrives, it sees that proposal number 1 has been accepted, 142, and this also, it sees proposal number 1 has been also accepted, 42. And you might think that at this point it just abandons proposal and says let 1 go through, but what it really does is propose the same value, 42, with this proposal number, which seems counterintuitive. So let's go and see the animation here. So um, nothing seen so far. 1 and 2 accept 1's proposal. Okay, so the acceptances occur at this point, which is 3's prepare request came after that. So 3 learns a majority accept of 142, and yet it proposes. Okay, and this is a question that I didn't find directly an answer in Lamport's paper, so I remember thinking a lot about this, and then I was on a walk and I think I figured out the answer, and you guys can find bugs in that answer. So anytime I deviate from Lamport, please go and think very carefully, especially when you're studying for your exam, because these kinds of arguments make your head spin, and I might have got something wrong. Okay, so the paper I read of Lamport doesn't really have a proof, so I haven't looked at proofs. It has an intuitive proof, and my arguments, I believe, are intuitively as strong. So we'll see. Okay, so this is Lamport does say that it reproposes. Okay, but he doesn't give a reason for this, and maybe the reason's obvious, the one that I've given, but it was quite subtle for me. So 3 reproposes 42 with its own proposal number. So we seem to be doing extra work. Sure, 42 will be accepted again and learned again, and so no harm done. But have you just wasted work? That's the question. Okay. So why repropose a majority of nodes have accepted 142? Think of failures. Okay, think of failures before learn phase completes at each node. And that's the argument I use. So I think I have a student discussion slide next. So let's go and see whether you guys can think of failures to suggest a solution, suggest a reason. So let's consider the situation without failures and with failures. Okay. So without failures, let's go and see how learning is occurring. We stopped at acceptances. Okay, majority of nodes have accepted, and hopefully this node will also accept. This node will not actually. Okay, so that's the key. So these two nodes have accepted, and if these two nodes broadcast goes to every node, then every node will learn 42. Okay, so if this proposal of 242 doesn't occur, and if no failure occurs, everybody will learn 42. Okay, so 1 and 2 broadcast accept response to 1. Okay, so one's accept request response goes to 1, 2's accept response goes to 1. At this point, it learns 42. Okay, and this happens at all nodes. Okay, these accept responses will go to 1, will go to 2, and will go to 3. Okay, even though 3 is not going to accept 1's proposal because it has gone and prepared itself for 2, for the proposal number 2. But that's the key here. Okay, so that's the reason why failures interfere with the situation, with the learning. So far, no failures. We've learned the values. Okay. Now let's say node 2 disconnects before accepted broadcast. Okay, before the broadcast of this accepted uh, state change. Okay, this acceptance. Okay, so 1 will not get this particular message. So it won't learn that. Okay, and neither will 2, neither will 3. 2 doesn't matter. 2 is disconnected, it's dead. So whether it learns or not doesn't matter. But this node will not learn this, and neither will 3. Okay. So you might say, okay, this value is not learned. Well, there's been a failure. But majority of the original nodes is still alive. And it's a little tricky what is majority right now. Is it majority among the alive nodes or is majority of the original nodes? Okay, and I don't think Lamport goes and mentions what it should be. But either way, majority of the original nodes exists, and certainly majority of the current nodes exists. So this value is not being learned, even though has not been learned through this route, um, even though there have been majority acceptances. Okay, the acceptance broadcast has not been sent successfully. Okay, so but there is this node 3. If node 3 accepts the value, then of course we will learn this. But node 3 has gone and prepared itself for 2, so it is going to reject 1's message. So they could learn it if 3 accepts 142 and broadcast the value to 1 and 3. Okay. So if it does this acceptance, when it sends its proposal, it would get it, there'd be no problem. But node 3 has promised to not accept proposal less than 2. Okay, because it's already sent itself the message 2 and it's responded by it's gone and stored this value. So node 3 rejects accepts request, and we will not get a majority. Okay, so if it reproposes 42, that will have the proposal number 2. Proposal number 2 is greater than equal to the proposal number for which this node has been prepared, which is that this prepare request, let's say 2 also arrives here. Okay, so it does arrive here. So it is ready for that too. So is this node. So they'll both accept 42 as long as it comes from 2, as long as it comes from 3 with proposal number 2. Okay, so that is why we need to repropose 42. Okay, that's my logic. I haven't seen it anywhere else, so I think this is sufficient logic for me to convince myself it's correct. But if there are holes, please let me know. Okay. So this is progress versus safety. We want to do this so that there is some progress. We could just go and say we won't repropose and then just hope that 1 will repropose 42 at some point after it times out, or 3 will go and propose its value after timing out and saying, hey, nothing has been learned so far, and we'll see timeouts working. But why not go and prevent such timeouts from having to occur? Okay. So we have now 3 conditions here. If some responding acceptor has seen a higher proposal number, abandon attempt. If no responding acceptor has accepted previous proposal, and that's true in the then propose attendant value. And now we see why we use majority here. If majority have accepted previous value, repropose it with intended proposal. If actually we need to go and use majority here also. Okay. So majority have accepted previous value, repropose it with intended proposal number. Okay. We need the majority here, right? We don't want to wait for just the first proposal number, first request that comes and says, no, I haven't seen anybody. Let's go and wait for majority of people saying we have not accepted, and then only do this. So majority is certainly needed here. But in Lamport's algorithm, he uses majority for all 3 cases. And that's another place where I'll deviate from him, and who knows whether I'm correct or not. Okay, what about, this is not all exhaustive conditions. What if some acceptors have accepted a previous value? What should be done? So it's not that the majority have accepted previous value, but some acceptors have accepted a previous value. Okay, what should be done? So, like I said, if under the stronger condition we reproposed, under the weaker condition where there are fewer proposals that have been received, we should probably repropose because failures can occur again. So this time, so far, its own response was sent later. Okay, so it saw 2 responses. It waited for these 2 responses before deciding what to do. It waited for these two responses before. Well, actually, yeah, it was this and this that it waited for before it proposed. Now its proposal comes earlier, so it doesn't wait for this response. It waits just for this response to come. At this point, it's got two responses. Okay, we were waiting for majority. So 3 gets its own response before it gets response from 2. Okay, so here's 3 and here's 2. It makes a decision at this point. So majority has only one accept notification, this one. This one doesn't have any accept notification. Okay. By the way, this should be 1 here. Okay. Because it has seen, depending on whether it should not be 2. It should be 1 or a question mark, depending on whether one's prepare request is gone or not. And I don't show you the arrow here, so just think of this being a question mark here. Okay, but the main point is we are looking at these two values, and so this is 142, and this is question mark, question mark, question mark. Okay. Same problems before. If 2 fails to broadcast accepted broadcast, fails to broadcast its accepted response, 3 will reject one's proposal accept request, and so it reproposes. Okay, so it doesn't send this message. This acceptance will not occur later, so we need to go and make sure that we repropose the value. Okay, so this is the same condition as before. Let's look at another situation. As before, 2 gets prepare request from 1 before 3, so 1 proposes and accepts 142. Okay. So it gets this prepare request after this prepare request. So it goes and responds with question mark, question mark, question mark, and it gets, so this guy goes and proposes this. Okay, so 1 proposes this and accepts it, and okay, so now let's go and see. Now 2 gets propose accept request from 1 after it gets prepare request from 3. Okay, so this is interesting now. 2 is not going to fail, but it's going to reject 1's accept request because it has seen this prepare request. This prepare request was first earlier arriving late. Okay, so both 2 and 3 will reject this proposal request. Okay, so both of them will reject it, and 142 will never be learned unless this goes and reproposes it. Okay. It could propose its own value, but it doesn't really know what 2 has done so far. Okay, so it doesn't really know that 2 is going to reject 1's proposal. So and because if 2 is going to reject 1's proposal, then we know that 142 will not be accepted by majority, but it doesn't know that. So it goes and safely, just for safety, it goes and reproposes 42 and says, look, if I don't know whether majority will be achieved or not. I haven't waited for all responses, so I'm going to go and repropose. Okay. If it waited for all responses, then we could avoid reproposing the value and propose our own value. Okay, again, this is my logic. See later when you guys study for this whether it makes sense or not. So 3 should repropose. Okay, that's what it does. So now my algorithm has changed. Else, if some have accepted previous value, repropose it with the intended proposal number. Okay, and we have pretty much completed our algorithm. Okay, with all the cases. By the way, the algorithm is described in 2 pages. But the cases are what take time. So as I mentioned in my mail, I might ask you to do tracing of various algorithms, And so that's why I wanted to go and focus on tracing here. And we understand better, at least I understand better with traces. Okay, maybe we haven't completed. What if responses indicate multiple values have been accepted? So maybe we haven't covered all cases. Because if some have accepted previous value, then repropose it. What is the it here? If there are multiple values that have been accepted. So as David indicated, we will accept the value with the highest proposal number. Which brings us to the next question. Can responses really indicate multiple values have been accepted? So can we have responses from different acceptors to our prepare request that have different proposal numbers associated with different accepted values? Given that we are reproposing a previously seen proposal number, is that really possible? Okay, so that's the next question. Can we construct a scenario where this really happens? Okay. So that's the next question. So let's look at this scenario. It's a bit more complicated than what we've seen before. Now we have site 2 also proposing. Okay. Site 1 proposes again for 42 and also still uses the same proposal number 1 it's used before. Site 2 proposes value 22 with proposal number 2. Site 3 again proposes 29, but this time with proposal number 3. So site 1 sends its prepare message with its proposal number. The message is received by itself and responds by saying it's seen no proposal before, so it's not accepted anything. It sends the message also to site 2, which has the same response. So site 1 has 2 responses with no previous accepted value. That's a majority of responses. So it proposes its intended proposal number and proposal value. It sends a message to itself, and since it has not promised to accept a higher proposal number, it accepts 1 and 42. Okay. Site 2 sends its prepare message in the meantime and sends it to itself, and it responds by saying that it's seen proposal 1, but it hasn't accepted anything so far. It sends a message also to site 3, and site 3 responds by saying it's seen nothing so far and accepted nothing so far. So 2 now has 2 responses with no previous accepted value. So it proposes its intended value with the intended proposal number. Okay. And it sends a message to itself and accepts it because 2 happens to be greater than 1. So its value is, it can go and accept this value. Okay. So it promised one that it won't accept any proposal number that's less than 1, and this is proposal number 2, so that's fine. Site 3 sends this prepare message to 1 first, which responds by saying that it has seen 1 before and accepted 1, 42, so 1 acceptance. Send the message to site 2, which responds by saying that it's seen the maximum proposal number it's seen so far is 2, and it's accepted 22 from 2. So now we have 2 responses that are both acceptances with different values being accepted, 142 and 242. Okay, so 2 different values, 2 different proposal numbers. At this time, site 3 has majority responses to its prepare request, and it has to choose between this value and this value. Since this proposal number is higher, it proposes 22 with 3. Okay. And to make this scenario work, I had to make sure that its own message got delayed by its thread so that it would actually see these two acceptances rather than see this information. Okay. And I didn't show you all the messages. So if this particular message, when this particular message arrives at site 1, it will go and accept a different value, okay? Because 2 happens to be greater than 1, it will go and accept 222 even though it's accepted 142 earlier. Okay? So this is an interesting situation where the accepted value can change at a node. Okay? So then the question becomes, are we really guaranteed that learned values will not change? Okay, since individual nodes can change their mind. Uh, this shows here that the, the message from site 1 that arrives late at site 2 with the proposal of 142 will in fact be rejected because of the promise site 2 has made to both itself first and then site 3. Okay, so far it has seen site 3's proposal, so it's going to reject this. And even if this message had arrived before this particular prepare request had reached site 2, it would reject this message because the proposal number is too low. Okay, so proposal later proposals can be accepted depending on the proposal number, and later proposals can be rejected based on the proposal number also. Okay, so again we have to go and visit this question, that are we really guaranteed that learned values will not change? And the key to getting this guarantee is the fact that some proposal will be rejected while some are accepted. Okay, and such rejections are going to make sure that learned values don't change. So let's try to answer the question more formally now, not through an example, but looking at the properties of our algorithm and try to answer whether we are really guaranteed that learned values will not change. Okay, so that's our next question. So here's the proof. Okay. Let M be the proposal number that first gets majority acceptances from some set of the value Vm. Okay, so Vm is the value proposed with proposal number M, and it has got majority acceptances from acceptors from the set AM of acceptors, okay, which is the majority in this total set of acceptors. Okay, so let this be the case. And we want to show that once a value gets majority acceptances, it will not change. So a value with minority acceptances may change, but not one with majority acceptances. Okay? So that's what we want to prove. And to prove that, let's look at the first value that got majority acceptances. That's Vm. Okay? And let M be the proposal number that proposed that value, that was associated with that value. Okay, and let AM be the set of acceptors that accepted that value. Okay, so let P be the next proposal that has majority acceptances from AP. Okay, so we can have, once a value has got majority acceptances, it might again get majority acceptances from a different proposal. Okay, so let P be the next proposal from which majority acceptances are is achieved. Okay, and let AP be the set of acceptors that actually accepted that value. Again, AP can be different from AM. Okay, two different majorities can be different. So let's try to first answer the question, is it possible for P to be less than M? Okay, we've seen that multiple values can be learned. Okay, so the question is, once a value has been learned from a proposal number m, can the value be relearned from a proposal that's less than m? Okay, so that's the first question. So here's the argument. P dot m is P less than m is impossible because AM and AP, they can be different, but they have at least one member in common. And when the prepare request went to that member, it had already accepted M. And that would have prevented the proposer of P to send its accept request because it would have seen uh, M and VM, so it wouldn't propose its own value because M happens to be greater than P. Okay, so we know this is impossible. So now let's go and see that whether we can break this rule by making M be greater than P, but proposing a value other than VM. Okay, so let again P be the next proposal that has majority acceptances, and let's try to see, given that P is greater than M, whether it would ever propose a value other than VM. Okay, whether it would propose its own intended value, or whether it would go and propose uh, the previously accepted value. And remember, P is the next proposal after M to get majority acceptances. Okay, so that's the next question. So here's the argument. P greater than M is possible, okay? But because AM and AP have at least one member in common, when P is proposed, it would have heard from this member, and that would have told the proposer of P about M and VM. And our algorithm makes sure that if it hears about a previously accepted value, it would go and repropose that. Okay, so we know that the next proposal after M would also go and propose VM if it gets majority acceptances. And we can use the same argument inductively and say the next proposal after P that gets, which might be Q, that also gets majority acceptances would also propose VM and so forth. So by induction, all n greater than m would accept, would propose VM, and since they would propose VM, they would the majority acceptances would also be VM. Okay, so that convinces us that the algorithm really works. So we complete the algorithm. We've said what happens to the prepare request, the prepare response. We also saw what happens with the accept request when it's sent and what data is sent with the accept request. And then this is the accept response. So accept request a proposal if its proposal number is greater than or equal to what it has seen in prepare request so far, and learner learns the value that has majority acceptances. Here's the problem that Lamport does mention. As before, 1 and 3 want to propose the values 42 and 29. 1 sends prepare request to 2, and then 3 sends superseding prepare request to 2. But when 1's prepare request arrived at 2, 2 hadn't seen a previous proposal, so it said fine with me. And the prepare request was also fine with 1. So when 1 decides to get into the accept phase and propose the value 42. When it arrives at 2, 2 says, sorry, I have now seen a higher proposal number, so I reject your accept request. Okay, and 1 says, fine, let me just wait for the higher proposal to arrive, and I'll learn that value. But 3 goes to sleep. Okay, so 3 delays its accept phase. And 1 times out, thinking that 3 is dead, so it decides to go and propose its value again. Okay. That prepare request arrives at 2. And now finally, 3 wakes up and starts its accept phase. Okay? But that is going to be now rejected by 2 because it's seen a higher prepare number. So 2 says, fine, let me wait for a learned value. But now 1 goes to sleep. Okay? And 3 gets fed up and sends another prepare request. Okay? So what's happening? For the proposal number 4 superseded proposal number 3, which superseded proposal number 2, which superseded proposal number 1, and we'll continue in this cycle because of the way processes are going to sleep. Okay? So we have a situation where no progress is being made. Okay? And we've seen 2 other situations earlier: starvation, where one particular process is discriminated against and makes no progress; deadlock, where everybody's waiting and nobody's making progress because they're in a cycle of waits. And here, there's a lot of activity, unlike deadlock, but no progress is being made. Okay, so this is called live lock. So the question is how to avoid live lock. Avoid live lock. What Lamport suggests is get a central process. Okay, so we're trying to get rid of central processes. It says let all the proposals go to a central proposer, which goes and mediates between them. And acceptors directly talk to learners, though, in this situation. And majority value will be the same. So what if this particular process dies? No problem. We can use another Paxos algorithm to go and choose a new leader. Okay, or we can go and use IDs to select the new leader. So so this will work out. And then he says, here's another problem. We have n nodes broadcasting to n nodes. So we have n square messages sent. So how can we reduce that? We can go and have all the accept requests go to a distinguished learner, which goes and sends the messages to every other learner. Okay, so now we have n accepted broadcasts other than n square. Okay, and again, if the learner dies, we can choose a new learner using another Paxos algorithm. Okay, this still seems like toy because we assume so far that the value is set a single time. Okay. So how to support edits? How do we go and change the value from IPC mechanism 1 to another IPC mechanism so far? So he says, look, let's assume a state machine in which some sequence of commands have to be executed in the same order at learners. So what we try to achieve consensus on is not the next value of this is this editable object, but the next command number to be applied to this editable object. Okay. So if we've seen the highest command number we've seen is 4 so far, we say, okay, we are probably 5, and most probably we will be 5. But let's figure that out, and let's go and propose 5 as your command number. Okay, so you send a proposal with 5, and if somebody else also sends a proposal with 5, then one of you agree. Okay? So we can have, and then somebody else could have seen 5 and proposed 6. So while 5 is being agreed on, 6 can be agreed on also in parallel. So we can have multiple Paxos instances be executing concurrently. And this is really what happens in production systems, whether it's Amazon, whether it's Oracle, whether it's Microsoft. I believe they're all implementing either two-phase commit or Paxos, and I believe they've all migrated to Paxos recently. That's why I was so keen for you guys to understand Paxos. This is something that I do believe you need help with in understanding properly. So that's what's going on here. Okay? And then a learner can sort of get commands in different orders, but it knows, assuming there are no holes in the command numbers, it goes and just waits for a previous command before it executes a future command. So it buffers commands and executes them serially. Okay, so we can get things to agree on. We can support edits of some state. Okay, so here's something else we haven't addressed: how to get unique proposal numbers. Okay, here there are 3 different nodes, distributed nodes, and the question is, how do we ensure that the proposals sent by them are disjoint and they don't repeat? So let's think about this a little while. Okay, this is a question that arises a lot in distributed computing, whether it's in Paxos, whether it is in Google Docs. it's an issue. Okay, so there's many consistency algorithms, and for different situations. So, what do you guys think? How do we get unique proposal numbers? Okay, so each replica can keep track of known proposals, and ID of new proposal can be one more than known proposals. Okay, that's my straw man. And you know, the problem here is that both proposers might have seen the same number of proposals, so they might go and uh, have two different proposals made by different replicas can have the same ID. This is Lamport's solution. He doesn't really he says, look, that's an implementation detail. I'm not going to spend too much time on it. He says, here's something. So at initialization time, we could have each um, node have a set of proposal numbers given to it, and it chooses those proposal numbers. And this algorithm was used in the X server. You guys don't know about X Windows system, but that was a famous Windows system in late 80s and early 90s. Okay, so that could be done. So ID of new proposal made by replica might be smaller than IDs of proposals it has already seen. So it may not get accepted, but it'll be safe. It may not. There might not be enough progress. So reproposals may not be accepted. So ID based. So each replica can keep track of known proposals, and ID of new proposal is. And Andrew suggested site ID and local proposal number, but then you can't compare two. How do you compare two different uh, tuples? And we could have the site ID be the most significant bits and the proposal number be the least significant bits. But then one site will always win over another site, regardless of when it went and um, issued the proposal. So what I did in my implementation, and I think I saw this somewhere else also, um, that ID of new proposal is number of proposals you've seen so far dot site ID. So make site ID the the lower bits. Okay. So ID of proposal made by replica will be unique and larger than the IDs of proposal it has already seen. Okay, so we get increasing proposal. Okay, so this is sort of the algorithm that I actually had in my code. Okay, it's 1 hour 15 minutes. We have covered the algorithm. We've covered the scenarios. I've hinted to you in the previous slide that I've implemented the algorithm, and as you've seen, I've gone quite deep into it, and I'd like to go a little deeper. It may or may not add more information. I think I'll finish in 10 minutes, but feel free to leave if you need to. But what I want to do is actually show you traces of code I've executed to just solidify the idea even more. Okay? So my traces are consistent with the scenario I had earlier. 3 nodes, 1, 2, and 3. They are proposers, acceptors, and learners. As it turns out, only one node 1 and 3 propose, and they're trying to decide on the meaning of life, which we want to decide on only once. Okay, and we'll see, who wins. And again, 1 is going to propose 42, and 3 is going to propose 29. And we'll see the various scenarios we've seen before. So I'm going to repeat essentially the scenarios we've seen before. Um, there's actually 30 more slides, 34 more slides, but I think I'll go quickly through them, but I might not. Okay, but I do want to finish that today, and hopefully I'll be fresh enough to interpret them correctly. So one difference between the traces I show you and the timing diagrams I showed earlier is that the traces are not quite as complete. Okay, so you see here that our responses contain 3 components: responses to prepare request, the last proposal seen so far, the last accepted proposal number, and the last accepted value. So question mark is going to be represented by -1. And this particular piece of information is missing. So we will only see the last seen proposal number and the last accepted value. And if nothing's been accepted, we'll send the value now. Okay, so I'm not sure why I omitted that particular value from the traces, but that's what we have right now. So So we want to look at one of the properties is that the proposer sends its proposal and value if majority acceptors have not yet accepted any value. Okay, and each acceptor accepts a proposal if its proposal number is higher than what it has seen so far. So I want to sort of show you these two things working together. So 1 and 3 find no previous acceptance, and 1 finds no previous prepare. Okay, so once accept is rejected by majority, 3's accept goes through. Okay, so 1 finds no previous prepare, so it goes there and sends a proposal. Okay, but its proposal doesn't go through. And 3, it's the higher number, so 29 should win. Now, how do I actually do this? I mean, there are all these timing situations, and those of you who made some progress with assignment 7, I've asked you guys to create certain conflicting and inconsistency situations with different consistency protocols. So how do you actually create these timing problems? And you can try to go and actually build some delays. But if you're working in Java, you can just put breakpoints in various phases and delay things. Okay, so I wanted once accept to follow 3's prepare, and of course once accept will follow 1's prepare, and 3 steps will follow 1 3 prepare. So I went and put breakpoints in start prepare phase and start accept phase, and I just released them in the right order so that this particular sequence of actions work. Okay, and this code is actually in the Git repository that you guys have access to. If you won't have time before the final. If you ever want to experiment with my implementation, and I believe I have implemented Lamport's algorithm and not the modification I suggested. So if you want to ever experiment with it, the implementation is there for you. So this is our first trace. Lots of lines here. And this is only showing you what happened at node 1. Okay, so the trace consists of both messages sent and messages received. And let's start here. Its user asks it to make a proposal for value 42. So it sends a prepare request with the value 42. It has seen no proposal so far, so it goes and chooses 1 as the proposal number, higher order bits of the proposal number, and its own ID as the lower order bits. Okay, so it sends a real number with the whole part being the proposal number and the decimal part being its ID. Okay, so it sends this request to itself and the other 2 nodes. Okay, so here's where it receives its own request, and here's where it responds to its request, and here's where it receives a response to its own request. Okay, and that response indicates that no value has been accepted so far, and the last known proposal number before this proposal was learned off was nothing. So this is 1 minus 1.0, and of course we need also a component that tells us if this value is an accept, what the proposal number there was. Okay, so this is the notification it receives from itself. It also receives a notification from node 2 saying it has seen nothing before, so that's good. Now we have 2 notifications. So it sends an accept request, a proposal saying I want to go and propose 42 with this value based on the prepared notifications I've seen so far. Okay, and it does, and this request is sent before it receives all the notifications, and 3 also says, look, I've seen nothing before. And after 3 sends that message, it makes its own prepare request, and it says, I want to propose 29 with this particular proposal number. 3 also has seen no other proposal before, so it chooses 1 for the whole number part, but it puts its ID for the decimal. Okay, and it's got 29. And to this particular request, this node 1 sends a notification saying, I have seen 1 proposal before, but I've accepted nothing. And in the meantime, node 2 goes and sends a notification to the proposal request sent by node 1 saying that, hey, I've seen node 3 before. Okay, it's prepared, and then accept. So every node sees the to prepare request before it sees any accept request. And so it says, look, we have a concurrency conflict. Okay, sends this message back to this node. It receives its own accept request at this point. Okay, after it's received this prepare request, and it tells it tells itself that, look, there was a concurrency conflict. Okay. So overall, based on the majority response it has, it knows that its prepare request got denied, and it won't bother. Its accept request got denied. Okay, so it learns about this, and if no other proposal is accepted within a certain time period, it can retry its proposal. Okay. In the meantime, after it sent its prepare response, it receives an accept request from 3 with 29. And it says, yeah, I've seen 1 before, but 3 is greater than 1. So I'll go and say, I'll go and announce that I have accepted this value. And it receives also a notification from 2 saying it accepted that value. Sufficient agreements have been reached. So, okay. So sorry, here it went and sent the notification to the whole world saying that it has received the value, it is accepting. Here it receives a notification from 2 that the value has been accepted. Here it receives the notification from itself. Okay, so here it's learning the value. So this is where it sends the accepted notification, broadcasts the notification. Here's where it learns about somebody else's broadcast, and here it learns about its own broadcast. So this is when consensus is reached, and it learns about. So it checks sufficient agreements, and it, as a learner, goes and changes its state to 29. It learns this particular proposal. Okay, so since it's learned 29, it's not going to retry and sending its rejected value. And some messages arrive later. So that's because we're only waiting for majority messages and messages from majority rather than from everybody. Even though we send messages to everybody, we don't wait for messages from everybody. Okay. So in that situation, 1 went and sent a proposal, but that proposal was not accepted. Okay, he sent an accept request, and everybody went and rejected it. Okay. Now it's going to not even send the second, enter the second phase. It'll abandon the accept request because of the way messages go. So in its prepare phase, it'll find a higher proposal number, and it'll not even decide to propose. Okay. Again, I have to play with breakpoints. Okay. So let's go and see. It makes a proposal right here. It receives a prepare request from 3. Okay. So it knows about this. It receives the prepare request from itself later, as it turns out. Okay. So prepare notification sent concurrency. So it gets it basically gets a concurrency conflict in the prepare stage, and it never makes a proposal, and it gets a proposal from 3 later, and so no accept request from 1, that has to be denied. Okay, so it doesn't get rejection, and so this is more efficient in terms of number of messages being sent because we caught the problem earlier rather than later. Okay. Here we're going to talk of reproposing. Okay, so proposer is going to repropose the majority value it has learned from the prepare phase as its own value. So 3 finds majority acceptances from 1 in prepare phase. Again, so we set breakpoints on those methods to make this case happen. Again, we're looking at site 1, even though this is case 3. And as before, site 1 makes a proposal of 42. sends a prepare request, receives its own prepare request, sends back a response to the prepare request, and receives that response. Okay, so that's the sending, that's the receiving, and receives a notification to its prepare request from 2. The both notification indicate success, so it goes and sends its accept proposal. Okay. And it accepts that request. So it accepts the request, of course, and every time you accept a request, you also broadcast that that acceptance. So it itself has not yet broadcast its accept notification, but 2 has broadcast its accepted notification. So as a learner, it receives this notification from 2. As a learner, it also goes and receives from 3 an accepted notification. Okay. And in the meantime, it sends its own accepted notification to itself, which it hasn't received so far. Okay. It doesn't need to go and wait for that notification to be received. At this point, it learns the value 42. Okay. So it's learned the value once. And then it receives from 3 a prepare request for 29 with proposal number 1.003. So we have to see in the next slide what happens. So that's this particular message here. And it responds to that request by saying, hey, 3 is greater than 1. So this is success. But by the way, I have already gone and accepted 42. Okay, I've seen 1 and I've accepted 42. So that prepared notification is received by 3, and 3 decides to abandon the value 29 and actually go and send a request, accepted request for 42, the same proposal number. Okay, so this is the reproposal. It says, fine, I'll go and it broadcasts its accepted notification. It receives an accepted notification from 2. It receives an accepted notification from itself that it broadcast, and it goes and changes the state again based on sufficient agreements being reached. So now we have this particular node learning the same value twice with different proposal numbers. Okay, so this is the reproposal. And of course, it receives some notifications after it has made up its mind. So why repropose with majority then? If we just went and learned it twice, and we saw that this is because of failures. Okay, so this is just review. When you guys study this will be fresh in your mind. So now I had to go and make sure that failures occur in the middle of this. You can imagine that was tricky. Okay, so we're going to do what I said earlier. A prepare phase will prevent node 3 from accepting the previous majority value of 1's proposed accepted by 1 and 2. Okay, so because prepare phase occurred, so 1's proposal was accepted by 1 and 2, but 3 will not accept it because of the way the prepare phase went. So if node 2 dies, node 3 will not get consensus value, even though majority of nodes 1 and 3 are alive and can converge to a value. So want consensus value to propagate to all acceptors of fault tolerance. So I had to go and play around with this. I said, okay, the star means I send my prepare message to everybody. This 3 means that I go and send, the 3 goes and sends the prepare request to only itself. Okay, not to the other 2 nodes to slow things down. Then star again means I send it to everybody else. And this accepted, I send to 1 and 2 and not 3. Prepare, I send it to 1 and 2 and not 3. I kill 2 in the middle here before it has sent this messages. And 3 sends its accept request to everybody. Okay, so I had to play around with this to make this work. Okay, so so that's what. Okay, so this is node 2. This is a node that will die, and it will die after it has sent the accepted notification to itself and 1, but before it has sent the accepted notification to 3. So 3 is not going to get consensus on the accepted value. Okay, so let's see that happening. It's broadcasts. It starts at broadcast. In the meantime, 1 has also broadcasted its accepted notification. It receives that broadcast from 1. As it turns out, three also got the proposal from 1, but 3 rejected that proposal. So it receives this concurrency conflict. It can't accept this point. It gets back its own broadcast here. So the value is broadcast here, but its thread receives it here. Now there are enough um, uh, acceptances, so it learns, it changes the state and learns this value. Okay? And after this, it goes and receives, after it's learned the value, it receives a prepared notification from 3, and it goes and says, look, I've accepted this value here, and then it dies. Okay? Let's look at 1. And 1 learns about 2's dying. Okay, so this is where you learn about this channel being disconnected. And you see 2 error messages here. That's just an artifact of my implementation. It's a peer-to-peer implementation. And what I did was, for every pair of nodes, I had each node connect to the other node. So if 1 and 2 are involved, then 1 connects to 2 and 2 connects to 1. So if 2 dies, 2 different channels are disconnected. Okay. So lots of text here, some text before the dying, some text afterwards. And you see before dying, it learns 42. After this process dies, again, it learns 42 from a smaller set of nodes. So that's the point here. Okay, and let's see this in depth, what's happening. So it receives its own accept request. Okay. It goes and broadcasts its accepted notification to all the nodes. Okay, and this notification is received by all the nodes 1, 2, and 3. It receives its own notification. It receives a notification from 3, the same notification that 2 received from 3. This also receives, saying that, look, this is a concurrency conflict. Okay, but it receives from 2 a message saying that it accepted the value, because it went and it saw that value. It received this proposal before it saw 3's value. Okay, if you notice in the last slide, 3's prepare request arrives at the very end. Okay, so it goes and changes its state to consensus to 42. So it's learned 42, and after it has learned this value, it finally receives 3's prepare request. Okay, so just like 2 received 3's prepare request late, so did it. And that request is proposal number 1.003, and the value is 29. It sends back a message saying that, yeah, sure, I will accept your value, but by the way, I have already accepted value 42 with proposal number 42. Okay, and I've seen this particular proposal. At this point, it learns that 2 has left the session. So so 3 goes and sends now, because it sent this particular notification to 3 goes and reproposes the value 42. So it receives this particular message. Okay, and it says, look, I'm going to accept the value. Okay, and also it broadcasts this value to everybody, and receives this value. It receives this broadcast itself, and saying, it broadcasts the value also, and it receives a broadcast from 3 saying that it has gone and accepted this particular value. Okay, now it's going to receive its own broadcast also, saying that the value has been accepted. Okay, the 1 and 3 are left. 3 proposes this value. It's the highest proposal number. So 1 will accept this value, 2 will accept this value. They'll both broadcast, and they'll both learn about these values as learners. Okay, but if you notice, I have the proposal state being changed before the last message from before the message from 1 is received. That's because it's kind of tricky right now. What's the majority? Are we talking of the majority of the initial nodes, or are we talking of majority within the nodes remaining? So just to make things a little complicated, this particular node does know that there's only two nodes left. So it says, well, and there's an even number of nodes left. It says, well, if I've got half the nodes, I'm fine. Okay, I'll agree. So this is a tricky issue. It could have waited till here. But just to show this issue, illustrate this issue, what should it really do at this point? I show it actually accepting this value before it receives a true majority, which is greater than half. Okay, so like I said, it changes the state now, and it learns twice as I intended. Once here, and here with the fewer messages because the number of nodes has changed. 3, on the other hand, learns it only once. It doesn't learn about 1's acceptance by 1 and 2. And 3 itself doesn't accept 1's value. Okay, and it will never accept 1's value because it has proposed its own value first. Okay? And that's why it has to go and propose the new value, because that value it will accept. So let's again just verify this. When it receives 1's prepared request, it has seen nothing, so it tells 1 that. When it receives its own prepared notification, it has seen itself. Okay, so that's still a success, though it has seen something before. It's not -1, but 1.001. And when it receives the accept request from 1, it goes and broadcasts concurrency conflict to both 1 and 2. So this value needn't be broadcast to everybody, like I think I said earlier, but my implementation does broadcast even conflicts to everybody, the whole world. Okay, so it won't go and accept 1's value. And it broadcasts this value and receives this value itself. Okay, so did 1 and 2. And it receives its own, it receives the prepared notification from 1 saying that, look, I have seen 42 and accepted 42, but I'm willing to go and accept your value too. Okay, and that's it receives that notification. So it goes and realizes 2 is dead. So it goes and proposes 42 as the value that it has seen before with its own proposal number. Okay, and this is interesting. 2 did go and send a prepared notification, a notification in response to the prepared request from 3, but this accept request was sent before the thread receiving this value in 3 actually got to execute. So this is a threading issue. So this value was sent before this particular process died, but was looked at later. Okay, so at this point the number of nodes is 2, so it goes and says, hey, that's enough. I'm not going to wait for the majority, so I'm just going to send my accept request. But with 42, and it receives its own acceptance, it broadcasts its acceptance to 42, receives its own acceptance. We have only 2 nodes left. Again, the tricky issue, what's majority at this point? So it goes and says, oh, I'm happy with this and I'm going to accept this value. And so that's what happens. Okay. And it will get 1's notification also later, just as 1 would have got 3's notification later, but doesn't wait for that. And had we gone and changed the algorithm to make it wait for that, then again it would have worked. But again, 3 learns this value only once. Okay. So why repropose with minority? Proposer reproposes the value of highest accepted proposal as its own value. So the value with highest proposal number may or may not become majority value. So that's interesting. It is possible for this node 2 to repropose a value, even though, as we saw earlier, the accepted proposal would never actually become a majority value. Okay. So node 1's minority proposal will not become majority value because 3 has seen a higher proposal number, but 3 does not know that it started accept phase, so reproposes. Okay, again I played around with breakpoints. So here's node 3, lots of text. Lots of messages sent, lots of messages received. The big point here is that we do have a reproposal, but we learn in node 3 the value 42 only once. This is what happened previously too in node 3 when it reproposed. But in that situation, node 2 had not yet sent node 3 its accepted notification. So before it died, so node 3 could never get the consensus value. Okay? This time, node 2 is alive, and yet it learns the value only once, even though it's a reproposal. Okay? That's a big point. So what happens here? It receives a prepare request from node 1, and it receives a prepare request from itself. Okay? And it responds to itself by saying that I haven't accepted any value, but I've seen this value. It receives a second prepared notification from node 1 saying, I've seen this value and I've accepted it. It's got majority prepared notifications. So it goes and reproposes the value of node 1 with its own proposal number. Okay? It doesn't use its own proposal number. It uses a proposal number, it doesn't use its own proposed value. Okay? And actually, had it used its own proposed value, that would have been fine, but it doesn't know that at this point. And the reason it would have been fine is that, so basically its value gets accepted, okay? Because all nodes, this is the highest proposal number around. And again, the reason why it could have proposed 29 and things would have been all right is that node 1's 42 would have been rejected by nodes 3 and 2. Okay, and so it doesn't see these rejections at this point, and so 29 would have been fine, but doesn't know, so 42 is safe. Okay, so we see these concurrency conflicts here to 42, and 42's value actually gets an aggregate denial, but this is something it learns later and not earlier. Okay? So each node learns once in the second reproposal. Nobody gets this aggregate, this conflict occurs at each node. So each node learns this 42 and not the first 42. Okay? This is a little different. And it could have learned 29, but again, our algorithm didn't know that, didn't have the information in advance. So 42 is accepted. So this is the last one we are going to. Reproposals can prevent any successful acceptance. So once first acceptance prevented from 3's first prepare, once first acceptance prevented by 3's first prepare, 3's first acceptance is prevented by 1 second prepare, and so forth. Okay. So again, I played around with breakpoints to make time. Okay, so we're going to see only part of the interaction here, just to reduce clutter. We don't see some of the prepare messages being sent. So this is node 1. It sends an accept request based on the responses it got to its prepare requests. And its request was rejected because between the time it sent its prepare request and it sent its accept request, node 2 saw the proposal from node 3. Okay. And so did node 1 actually. So both node 2 and node 1 refuse its accept request. So it gets a denial. Okay. And it waits for a while for 3's value to be accepted, but 3's being lazy or 3's messages are getting delayed. So it goes and reproposes 42. Okay, and says, I'll choose a higher number. And this is the number it chooses. So it's already seen 1. So it chooses 2 this time and puts in the decimal part its ID and sends a prepare request for that, okay, to the whole world. And people are willing to go, and it's the highest number so far, so people are willing to go and um, uh, it gets back a response saying that we know of this particular proposal, but if your proposal will be accepted because it's a higher number. And because the other nodes have seen this proposal, before they got the accept request from node 3, so it gets these 2 notifications here. And this is the situation I was talking about. So it proposes, it sends an accept request for 42 with the new proposal number. And in the meantime, um, node 3's accept requests are getting rejected because of this higher number proposal. Okay, so that's what's happening here, and now you can see this cycle repeating again and again. Okay, so 3 doesn't get 2's it doesn't learn about 2's value quickly enough. So it goes and reproposes its value 29 with a higher proposal number, and that will cause this proposal to be not accepted. And again, if they delay, if both nodes delay, this will go on ad infinitum. Okay. So here's a summary of the algorithm in Lamport's words. So what he's saying is that we want certain constraints. We basically don't want the same value to be learned multiple times. Okay? And to ensure that, to ensure this happens at the learner side, um, we can make certain conditions true at the acceptor side. And the condition true at the acceptor side is that if a value v is ever chosen, then the acceptor never chooses another value. It never accepts a different value. Okay. And to ensure this happens, we can put some constraints on the proposer side where it says, where we saw the 2 conditions, that it proposes its value if no acceptor in a majority of nodes has accepted any proposal number less than it, or if v is the value, or it goes in, and in that case it can go and choose any value, including its intended value. Otherwise, if it does get in set S some previously proposed value, then it picks the value that has the highest proposal number in that set. Okay, so this is essentially summarizing what I said. And this is an additional constraint at the acceptor, that an acceptor will refuse values, um, uh, refuse to accept a value if it has seen a proposal with a higher number earlier. Okay, and this is Lamport's algorithm verbatim, and you can check whether what I said was consistent with this or not. And we are now in the second last slide, I believe. And I just want to make a summary of all the mechanisms we've seen for consensus. So what you guys did so far in assignments 1 to 5 is the asynchronous consensus. Okay, you proposed, you learned. Then what you've done in what you're doing in assignment 7 is a centralized consensus algorithm where you have propose and remote propose. In between, I talked about a synchronous consensus mechanism where there's only one person proposing. Okay, so here you sort of have to go and invalidate the values also. So we not only have the operations of propose and learn, but we also have the operations of accept and accepted. Okay, so accept is this um, uh, request that comes in, and accepted is your response. Okay, and in Paxos, what you have also is prepared and prepared. Okay, so we have another phase here where you not only have the prepare request coming in and the prepare response going. I mean, we have these 2 steps, plus we have all of these steps also. This step is needed only in the efficient one where we're trying to make sure that we don't get into a loop of prepares. live log or prepares, or we want to reduce the number of messages. Okay, so this is just putting things in context. Okay, and I still see 12 participants, which is good. I don't know how many of you guys can still focus here, but I did want to finish this today. So here's some text which summarizes all the consensus algorithms we've seen so far. And this is stuff for you to look at later. Okay, and I believe that is the end.